We have learned about the probabilities of states, but still we don't know how to calculate many variables. From the probabilities we can calculate the internal energy. It's here. The internal energy is the sum over all states of the energy of such a state times its probability. So let us say we can calculate the internal energy. But it's not enough. You know that in thermodynamics it's quite common to work with small changes of variables. So we'll do same process here. We put the operator d in front of this formula, and here we have such a product. So the result of a small change is split into two terms. This is the sum of weighted by probabilities changes in the energies, and the second term is again the sum, and here we have changes in probabilities. So once again, this means that the energy level change a bit. Why and how we'll see later. And this means that the probability of state change. And we know this equation. This is the first law of thermodynamics for only pressure volume work included. This is the pressure volume work, and this is the element of heat, which for reversible processes can be replaced by temperature times the element of entropy. So the first term can be related to this concept that energy level changes if we change the system in some way. For example, we can change the volume of the system. If we change the volume of the system, we change the energy level, certainly. And this is essentially the work, the mechanical work. We can relate it to the pressure volume work. You've done it in the lectures, but the principle is that this term, that is this term, corresponds to work. Okay, let's leave it for now. Let's take care about the second term. Here we have entropy. Entropy is related to heat, and here we have a formula where we change the probabilities. But if we have a system and put some heat to it, heat it up, so we certainly change the energy, change the probability. So it's likely that this term that corresponds to heat will correspond to this term. Okay, it seems to be simple. So we take these two terms and let's do some mathematical consequences of it. So what we know? We already know that the probability of state psi is given by the Boltzmann formula. We can write it in such a way. Beta is the inverse temperature. And the trick is, because we want to calculate this term, that we express energy by probability. Like inverting this equation. And also we know that for probabilities this normalization should work. So let's try to calculate this term that we know that it will correspond in some way to entropy. So simply, this is this. This will be inserted from here. And we have a sum of two terms, and this is a constant. And what I am saying is that by taking a derivative of this or differential of this, the sum of differentials is 0. You can see it here. Because d of unity is 0. So this cancels out, and what's left here is this term. Here is reshuffled, and this is the rest. And now I'll do another trick. I am saying that this equals this. To prove it, I'll do it in the opposite direction. Or I am saying that this term, if I apply d on it, splits into third terms because I have a product. So the first term is pi of psi with a differential is here times this logarithm. And the second term is this pi without d, and now differential of this logarithm. But the differential of logarithm is the derivative of it, that is 1 over pi times the differential of pi. And now it's quite easy to cancel this out and use this again. So this term is 0. So this proves that originally this term it is the term we want to calculate, which is here, which should be equal TdS equals this. And now I make the comparison and I calculate S from it. And this is the result. The entropy is minus Boltzmann constant times this. To be exact, I compare differentials. So to be precise, there should be certain constant here as 0, because I compared only differentials. But we should think a bit. For example, we can think about the entropy of a microcanonical ensemble. Any other constant here except 0 is not acceptable, because I would get, on combining systems of one state, I would create entropy, and it's not possible. So this is a result for a canonical ensemble. I can now make a trick. Well, it can be done in a better way, but let us say I have a system with only several energy levels which are close together, so that these probabilities are similar. And in this case, essentially, I am getting the microcanonical ensemble, and I have pi given as 1 over the number of states, and I put it here. So here I will have 1 over W, and here I will have minus logarithm of W, and the sum of the same terms cancels out, and I'll get this final formula. This is a well-known Boltzmann equation for entropy. It is so well known that it is engraved on this tomb in at the cemetery in Vienna. Here you can see this famous equation. Okay, so this is the Boltzmann equation for entropy, very important one. Also, there is one note here. Now here I consider the system in equilibrium. I can consider a system where there are transitions between states. These transitions are given by certain rules. I have certain probability how to get from one state to the other state, and I have a sort of symmetry between these two transitions, that is from A to B or B to A. And if I do some mathematics about this, I'll get that if I have a system which is not in equilibrium, during the time evolution of such a system, this equation must be true. That is the entropy growth in time. This is the famous Boltzmann H theorem. It's called H theorem because originally the entropy was denoted as H, and I guess it even had opposite sign or something like that. Now we are using S. And there's time for a case study, let us say, about this theory, whether it can give something that perhaps you have heard. Let's consider an ideal solution, maybe liquid or maybe a crystal. We also have ideal crystal solutions. That is, we have such a lattice of different atoms, and we will assume that the energies of neighbors are all the same. That is, all configurations have the same energy. And the question is, what is the entropy of this? Or in other words, what is the entropy of mixing? So we will mix N1 molecules of type 1 and 2 molecules of type 2, and the number of possibilities is given by this combinational number or by factorials in this way. To explain this, let's assume first that all atoms here are numbered. If they are numbered, I take the first molecule and put it anywhere in the lattice. I have n possibilities to do this. Then I have n-1 remaining molecule, so I take the second one and put it in any other place, but one is already occupied, so I have n-1 possibilities. And so on. I have n factorial possibilities how to place numbered or labeled molecules on a lattice. But I do not have labeled molecules. I have only blue and red molecules. So I will think in the same way which configurations out of these are the same, because all red molecules are indistinguishable. So I can choose one of n1 red molecules, and I have n1 possibilities, the second one n1 minus 1, and so on, and I must divide by this. So this is the number of possibilities. And there is a bit of mathematics here that I will skip in detail. So this is clear how it's defined, and now I will do an approximation. I will approximate the factorial by this so-called Stirling formula. Here is the simple version, which is good enough for us. Below you can see a more accurate version. Such a formula can be obtained by replacing the sum here. The logarithm of factorial is logarithm of such a product which was written here, that is sum of logarithm of term, that is logarithm of 1 plus logarithm of 2 and so on. I will replace this by this integral, and by the integration per parts I will get the result. And if I insert it here, I'll get in the end of the day this formula for the entropy of mixing. And I believe you are familiar with this formula. Usually in the first course of physical chemistry, such a formula is obtained by mixing ideal gases, that is from classical thermodynamics. Here we've derived this formula from the Boltzmann formula for entropy. But don't bother about details about this. Anyway, I put plus here, which means that it's something, some example edit and not the mainstream of this lecture. But this is a bit more, bit simpler. The case of the so-called residual entropy of crystals. Actually, there is an interesting story about it. In the 30s, the statistical thermodynamics and quantum chemistry was quite new, and people didn't believe it too much. And there was a problem. People measured the entropy of water vapor using classical thermodynamics. That is, they use the third law of thermodynamics. They set the entropy of ice to 0. Then they integrated the heat capacity of ice. You know that change of entropy is given essentially times by something like this, the heat capacity over temperature. Then they added the entropy connected with the melting ice, which is just the melting enthalpy divided by the temperature of melting. Then they integrated the similar formula here for water. Then they added the enthalpy of vaporization, and they arrived at the entropy of water vapor. But there is also the Boltzmann formula and statistical thermodynamics. Okay, it's not so easy. You must count rotations of molecules and translation degrees of freedom. So there is some quantum mechanics in, but it's doable. People did it. And the problem was that these two values for the entropy of vapor didn't agree. And it was a problem. Those times people didn't believe statistical thermodynamics. They thought, okay, something's wrong with this theory. But it wasn't the case. The case was that those experimentalists didn't take into account chaos that is in water ice at 0 temperature. This chaos was explained first by Linus Pauling. You know Linus Pauling from other works in chemistry, but anyway, here he derived this entropy of ice. But before I will tell you how Pauling did it, we'll take a simpler crystal. And a simpler crystal is, for example, a crystal of carbon monoxide. I know it's a strange crystal, but the same problem with the entropy appears there. If we cool down carbon monoxide, it makes a crystal, but at the temperature of freezing, there is a chaos in the orientation. The molecules of carbon monoxide are a bit elongated, so in a crystal they are arranged in one direction, but at the same time the dipole moments of carbon monoxide is relatively small, so that the orientations of these molecules are essentially random. And this randomness has certain entropy with it, and we can calculate this entropy. If we calculate the so-called residual or also configurational entropy, we'll take, let us say, 1 mole. We have 2 possibilities for each molecule. We have 2 directions. If we have Avogadro number of molecules, the number of possible configurations is 2 to the Avogadro number. We have logarithm, so this is a double, we call it double U, number of all states. And if we calculate this, we'll get that the molar entropy of carbon monoxide, or also nitrous oxide, is the gas constant times the natural logarithm of 2. Actually, for water it's a bit more difficult. I will show you here how the chaos in a crystal of ice looks like. We have a crystal where there are hydrogen bonds, ideally, or there are no defects, or there are little defects in this structure. That is, all molecules are assumed to be bonded, but still there is a chaos. And to calculate the chaos, Pauling assumed that every water molecule has 6 orientations in the crystal of ice. Because we can move both atoms, and we have 2 it has a tetrahedral arrangement, and we have 6 possibilities how to put 2 hydrogens to this sp3 hybridization tetrahedral. Okay, but if we did this for every water molecule, we would create a lot of cases where we wouldn't have a hydrogen bond. We could have 2 protons at one oxygen bond, or no protons, that is 2 electron pairs. So it would be very wrong. So we can say at the simplest level that the hydrogen bond in this reasoning is wrong with probability 1/2, and with probability 1/2 it's good. That's because we have actually 4 possibilities. We have hydrogen bond with this hydrogen, so here is the donor, or we have this, and we have non-hydrogen between them, and we have 2 hydrogens. These are defects which are they are possible with very low probability. We assume they are not, and these are 2 good possibilities. And let's assume we have 1 mole of ice, and totally we have 2 times the Avogadro number of bonds in the mole of ice. 2 times is because to be bonded is a pair property. That is, we around every oxygen we have 4 other oxygens, 4 neighbors. But it is a pair property. That is, we have totally 2 times the number of oxygens is the number of bonds in a mole. And now we can apply the Boltzmann formula. That is, the molar entropy is the Boltzmann constant times the logarithm of this factor to the number of molecules divided by this factor, or multiplied by 1/2 to 2n, which we have here. This is approximately logarithm of 1.5 times that Avogadro number. I will get this. And this is the experiment. This is a better value. Actually, this is not exact because of the circles. So this predicts 1.5. This is a better value, but with the accuracy of the experimentalist, this is okay. And if this residual entropy of ice was included in the thermodynamic calculation, the final result was an agreement with statistical thermodynamics and quantum theory. One more example. I guess this example is quite instructive, and I would say quite deep, because it tells us what are the driving forces in nature, in our lives. Entropy can be defined for information, and you know that we have DNA in our bodies, and DNA contains 4 bases. Let us say that they are distributed equally and randomly. Of course, it's not true, but we would like to do a simpler calculation, and it means that we can calculate the entropy, the configuration entropy or information entropy per 1 base pair. Because we have 4 possibilities, this entropy is here. If we express it in molar units, we get here the gas constant. But entropy isn't so important. At the temperature of our bodies, we can calculate the corresponding change of the Gibbs energy. Perhaps I should write here the formula for, let us say, differential, or perhaps I will write just the definition for it's enough here from the enthalpy. The differential is enough here, is defined right here. So if we are at constant temperature, you can put some delta here. Of course, we have some change of enthalpy too, but here we calculated the change in the information entropy. So to transform entropy into energy, or if you wish, change of the Gibbs energy equals the reversible work, we multiply this just by temperature and perhaps at the minus sign. It depends on how we interpret it, and we'll get this result. Some energy per mole, which is equivalent to the chaos given by 4 possibilities in distributing base pairs in DNA. It may be useful to compare this to the energy unit of our cells, which is the energy of the ATP-ADP reaction, which in the usual conditions in a cell is here. So we can see that this is a huge energy. It's about 10 times larger than this energy. But on the other hand, we wish that our bodies synthesize DNA accurately, without any error. So we need energy surplus to do this. And the interpretation of this value is that this is the minimum energy needed to maintain order. With on the other side of the order is chaos. So you may have certain sequence of chemical reactions that synthesizes DNA from bases that we have somewhere, and it will consume certain energy. It can work and synthesize a random chain, but we don't want to have a random chain. We want to have a chain with certain information. So we must add energy to synthesize our DNA in the correct order. And this is the theoretically minimum value of energy we need to maintain order. Actually, we will need much more, because nature is never so efficient as regards thermodynamics, but this is a minimum value. So this could be okay. We can proceed with calculations and estimate. Let us say that if we have 10 times this energy, what is the probability of making a mistake, a mutation, and so on. It can be done, but I guess this principle, it is an extension of this principle. Simply we need much more than what we have calculated here, so that our bodies work well and synthesize DNA in the proper order. And there is time to finish thermodynamics. We calculated that in the canonical ensemble, that is a constant temperature, the entropy is given by this formula. We also know that this probability, Boltzmann probability, can be expressed in this way, where beta is the inverse temperature and alpha is a parameter that maintains that the sum of all probability is unity. It's a normalization constant. Again, we take this, we have logarithm, so we insert the logarithm of probability here and calculate. The sum of alphas is simply here, because the sum of this is unity, and here we have the weighted sum of energies, so that we'll get the internal energy here. Beta is 1 over kT, so kB cancels out and absolute temperature is here. In other words, we have a relation between entropy and the internal energy and alpha. From this we can calculate alpha like this, and we can see that what we are getting here is the Helmholtz energy, and it's an important result. It means, again, when we go through all this from the definition, because we have alpha from here, we'll find that the Helmholtz energy equals minus Boltzmann constant times temperature, time minus Boltzmann constant times temperature, times the logarithm of this huge sum. Actually the sum which is used for normalizing. And this sum is called the canonical partition function, also the statistical sum. And you can now see the analogy with entropy. In the microcanonical ensemble, the entropy is just the Boltzmann constant times the logarithm of the number of states. The more configurations, the higher entropy. The more configurations, the higher chaos in the system. We have more probabilities how to reach one macro state by microstates. So, perhaps one example was here. The bigger piece of a crystal, the higher mixing entropy. Here we have something a bit similar, but instead of the number of states which we have here, we have the number of weights. That is, it is a similar sum over all states, but there are states with low energy where the Boltzmann factor is almost unity. So it's similar like here, but but there are also states with high energy. Then the Boltzmann factor is almost 0, and it doesn't contribute to this sum. So we can say that this statistical sum is something similar. It's this number of all states, but we count only the number of accessible states. And an accessible state, it's not 0, 1 dichotomy. It's maybe a state which is fully accessible with very low energy, partly accessible with some moderate energy, and not accessible at all with very high energy. If we have the Helmholtz energy, we can calculate everything what we need. We can calculate pressure. Perhaps I will write here the basic fundamental equation for the Helmholtz energy, which is here. So from this equation it follows that temperature entropy is given by derivatives. Actually this is more important for practical calculations, and the internal energy, enthalpy, Gibbs energy. Okay, we have a very general expression for the canonical partition function. It contains the sum of over all states. But if we describe our world by classical mechanics, like positions of atoms and momenta, then we must replace this sum by integrals. It's not so difficult as you would assume. We know that the energy, sometimes we use symbol H as Hamiltonian, but it's not important at this moment. And this energy is a sum of the potential energy and the kinetic energy. The potential energy of such a classical system is the sum of energy terms and is a function of only positions. There are no momenta and velocities in the potential energy. The kinetic energy is a sum of kinetic energies of individual atoms. So it has quite a simple form. It's a sum of something. This may be quite complicated. There may be pairs of particles interacting and so on. Thus it is possible to replace the sum which defines the partition function, the canonical partition function, by this integral. So instead of summing up over all eigenstates in a quantum sense, we will use the integral. And we will integrate over everything that we have. We have positions of atoms here, and we have momenta. I'm using here momenta. I could use velocities. At this level, it doesn't make any difference, but it's usual to use momenta. Then the formulas are simpler. Let us say it in this way. And here we have this Hamiltonian h, which is a function of so many variables. Well, one would say this is the result, but there is something more here. There is a factorial. Why a factorial? Because if we have n indistinguishable n particles, let us say n atoms of argon or something like this, then these particles are not distinguishable, or argon atoms are the same. So we would count the same conformation many times, because if we exchange two atoms, we should get the same. So we must divide this by the number of atoms factorial. This means we have just one type of atoms. We had more types, we would have a product of factorial here, but I would like to keep this as simple as possible. So this is just for a simple liquid, let us say, just an example. And also we have here something a bit more strange, the Planck constant. So why is this? So one answer is that we must have this statistical sum without any unit. This is unitless. This integral has units. Here we integrate over volume, here over momentum. So we must put here something that would reduce the units to unity. And the Planck constant to Cn is just the correct unit. But of course it's deeper. It's deeper because if we take a particle in a box, take many and calculate the partition function first for one particle in a box, that is, calculate the energy levels, and then take n such particles, it is this vector, we'll get a match. We must do some approximations, like that the box is large enough so that we have enough energy levels so that they are smooth enough, and we'll get this result. I guess I have in the end of this talk calculation of this, but I will not go into details. So just you should know that there is something here which should maintain the dimension, and that we also get from quantum mechanics. I should also say that this is called sometimes the semiclassical partition function because this approach fails if quantum effects are important. I will come to it later. So it is not the full truth, it's just an approximation of the fully quantum description. And now look, we have an exponential of a term which is a sum of several terms. It is the potential energy and the kinetic energy, and also the kinetic energy is a sum of 3n terms. That is, this exponential can be split as a product of several terms, and we can integrate every term separately. And that is what is done here. Particularly, we have 3n integrations over momenta, and each term looks like this. Here is the kinetic energy. By dividing by kBt, we'll get with the exponential of the Boltzmann vector. So we have this term here, and we integrate. And if we evaluate this integral, it is the so-called Gaussian integral. You perhaps have heard about it, but I am not going to go into details here. We'll get such a result. And we have 3n times. And the final result of this partition function, z, is here. it is Q. Q is what was left. What was left here depends on the potential energy. Here there is the factorial is the same, and from 3n such terms we'll get this result, which is usual to write in the form which is given here using lambda. Lambda is the de Broglie wavelength, and here's the formula for it. The meaning of this wavelength is that it is the de Broglie wavelength, or the length of de Broglie waves in the spirit of quantum theory at a typical particle velocity which it has at a given temperature. From this interpretation we also get the meaning of this lambda and what we need to fulfill so that these formulas can be used. So the requirement is that the lambda must be much shorter than is a typical atom-atom separation. I can make a small drawing here. We have particles, okay? But from the point of view of quantum theory, these particles can be replaced by certain waves. The classical approach is accurate enough if this wavelength is much shorter than is the typical distance between particles. Back to this Q. This Q is called the configurational integral because we already integrated over momenta. And what's left there is the integral of the potential energy. I now change the symbol a bit. Instead of the potential energy, I am writing U as a function of atom positions. And if we evaluate this integral, again we have the Boltzmann factor here, we'll get the configuration integral, and from this the final partition function. Also, if we have a static quantity, that is quantity that doesn't depend on the particle velocity, it is, for example, pressure, but it is not viscosity, for example, then the mean value of such a quantity can be expressed in a simpler way than for a general quantity, just using integration over positions of all particles times the quantity times the Boltzmann factor. And this is a normalizing factor. And I guess an example about the de Broglie wavelength will be useful here. The task is to calculate lambda for liquid helium at low temperature. And we should compare it to the typical distance of atoms in liquid helium. And here is the density of liquid helium. So let's calculate. Essentially, lambda is obtained by inserting data to the formula. I should stress that you are not supposed to memorize these formulas, but you may get a task or an exercise or homework or a task in an exam with such a calculation, but the formula will be given to you. Okay, so the de Broglie wavelength we'll get by this formula. So let's insert everything in the SI units, the Planck constant, here the mass of molar mass of a helium atom, which is 4 grams per mole. So I'm inserting here 0.004 kilograms per mole. The Avogadro number, the Boltzmann constant, and temperature is 2 Kelvin, and this is the result. The second part is to calculate the typical distance of atoms in liquid helium. So this typical distance can be obtained assuming that all atoms are placed in square lattice or cubic lattice. It's of course very simple approach, but we are doing order of magnitude calculations. So this is volume per one atom, and the volume per one atom is the mass of this atom. This is the ratio of the molar mass over Avogadro number divided by the density. Again, we'll put the same molar mass in kilograms per mole of helium, Avogadro approximated, and the density converted to kilograms per cubic meter. And this is the result. And we can see that lambda is longer than the typical distance between atoms. And it means that we cannot use classical mechanics. We could use classical mechanics at much higher temperatures. At much higher temperatures, this would decrease. For example, if instead of 2 Kelvin, we had here, for example, 200 Kelvin, it's close to the normal temperature. We have square root here. Here we would get less than 1 angstrom, that is 0.6 times 10 to minus 10 meters, and it's several times shorter than this. So at this temperature, the classical mechanics should work, perhaps not perfectly, with some small deviations, but quite well in practice. So let's now proceed or using these formulas for the simplest case we can imagine, and this is the monoatomic perfect gas. So let's calculate the configuration integral here. It's given here is the formula. We have the exponential of the potential, but for perfect gas this energy is zero. We don't have any potential energy between particles of ideal gas. They don't interact. So we just integrate this exponential of zero, it is unity, by all coordinates we have. And each integral is over volume of the system. And it's integrated by its element, and we have in total n such elementary integrals over volume. So we have volume to n. So it's a clear, easy result. And now the partition function is q, the configuration integral, divided by n factorial, and lambda to 3n. Well, we have a factorial here. It's common using the Stirling's formula. I showed this Stirling's formula some time ago to replace this factorial by this. It's good enough for us. So let's do it. Lambda is left here, and we know that if we take a logarithm of this partition function with some factor, we'll get the Helmholtz energy. So it's now easy to insert and get the Helmholtz energy, and this is the result. Actually, what I did is that all n's which are here I put in front of, because I have logarithm here. So this is the result. Perhaps it is worth noting that this uppercase E is the Euler number, 2.718 and so on. And this italics E is the elementary charge. It's not here, but sometimes we get formulas where there are both quantities and we should distinguish them. So they are distinguished by typography. We have the Helmholtz energy. How to calculate pressure? We calculate pressure by taking the derivative of the Helmholtz energy at constant temperature with minus sign. So let's do it. It's actually quite easy because we have volume only here. So we have the prefactor. Actually, we have minus here, so minus minus gives plus. So this is the prefactor with good sign. All this isn't necessary because logarithm of a product is the sum of logarithm, and this doesn't depend on volume, so the derivative is 0. So we have the derivative of volume, it is 1 over volume. So this is the result. This result shouldn't surprise you because this is the equation of state of the ideal gas. So it means that we calculated correctly. In the same way, we can calculate the internal energy. We already have the Helmholtz energy here. So we put it here, plus temperature times entropy. And entropy, if we have the Helmholtz energy as the basis, is obtained as the derivative of the Helmholtz energy over temperature and constant volume. Perhaps I will write again here the fundamental equation, sometimes called the Gibbs equation of the Helmholtz energy, which is minus PdV minus minus S dt, like this. So from this equation we are getting this just by dividing a constant t, and also this. Okay, here the calculations are a bit more difficult or tedious, I would say, because we have temperature here, but also temperature is hidden in this de Broglie wavelength. So to calculate this derivative, we need to differentiate these terms. So it's a bit complicated, but trust me that the result is what you expect. That is in agreement with the equipartition principle. It means that we have calculated correctly. We got both formulas that we know are correct, and actually we started with these formulas. It may be also interesting to calculate the chemical potential. The chemical potential, we must proceed a bit further. This formula will be amended by similar formula containing the change of particles, something like this for one substance. Here it is, if this is in more units, if we use molecules, and then we will have n, then the Helmholtz energy is per, not more, but per molecule. But anyway, we take the derivative against the chemical potential, and again there are two terms, but it's not so difficult, so it can be calculated, and we'll get the chemical potential of a monoatomic ideal gas. Also, we can recalculate this chemical potential using the Helmholtz energy and the PV product. This is the definition of the Gibbs energy, essentially. And the chemical potential equals the molar Gibbs energy for pure substances. So if we do this, we have one term here. The sign is correct because I replaced numerator and denominator here, plus PV, which we take from here, or this equation of state, and we'll get the same. Perhaps I should emphasize that the chemical potential here is with respect to the standard state of a free molecule at zero temperature. It's sometimes called the absolute chemical potential. In chemistry, we often use the chemical potential with respect to some other standard states, but let's be happy with this for now. I will provide some details later. And I will skip this. If you understand a bit quantum chemistry, you can verify that for quantum ideal gas of molecules which are indistinguishable, and with this approximation or this assumption, we'll get the same result as we assumed or guessed before. So thank you for the attention.